Welcome to EDU World Space.
Hello. In this problem, we have a baggage carrier at an airport, and we have a worker throwing different pieces of baggage onto it, and we're going to have to figure out how much energy is lost in the system after each bag is thrown onto the baggage carrier. Now we have a 50-pound baggage carrier. The worker at the airport is going to throw horizontally, initially, a 30-pound object onto this L-shaped baggage carrier at 9 feet per second. And then shortly after that, they're going to throw a 40-pound suitcase on the suitcase carrier at 6 feet per second. And so the question is, how much energy is lost, A, when this 30-pound object hits this carrier, and then B, when the 40-pound object hits the carrier. Now, what do we mean by that? Well, if we consider all of our mass here, the carrier and both of the suitcases, as one whole system, what we can do is we can count up all of the kinetic energy that's in that system in one state, and then count up all the kinetic energy in that system at a different state. If we take the difference of those two and find the change in kinetic energy, that's going to give us how much work is associated with non-conservative forces. And a lot of times, those things like friction and deformation and turning that energy into sound and heat, right? That's the sort of thing we're calculating here. This is particularly relevant because also our system is not changing its potential energy at all, right? Nothing is changing its height in the gravitational field. There's no springs involved or anything like that. So we just have changes in kinetic energy, and that's overall going to tell us the amount of energy we have lost due to sound and heat as we throw these suitcases on this baggage carrier. So what do we need to do then is we need to figure out the kinetic energies of our system at the different times that we care about, right? So for part A, if we want to figure out the energy loss due to the first suitcase being thrown on there, so the 30-pound one, right, we need to find out the change in kinetic energy from the state, we'll call it state 2, which is right after the 30-pound suitcase has been thrown onto the, 50-pound suitcase carrier. And then we need to figure out T1, which is the initial state, which is just the state where the 50-pound carrier is at rest, and our worker has just thrown that 30-pound baggage. So we need to compare the kinetic energies there. But in order to do that, we're going to need to figure out what the velocity of the 30-pound suitcase combined with the 50-pound baggage carrier is going to be the instant after that 30-pound object hits the 50-pound one. So to do that, we're going to need to use our conservation of momentum, right? So, and remember, ultimately, we're trying to figure out the velocity of our combined system here. Let me use a little different color here. So we're going to be, for now, we're caring about this sort of scenario where our person has just thrown the suitcase onto the 50-pound suitcase carrier. So we need to figure out what the velocity of this thing is going to be right after the 30-pound suitcase hits it, so that we know what the velocity is and therefore what the kinetic energy is. So to do that, we'll use conservation of momentum. We know that initially our total momentum in the system is just going to be the momentum from our 30-pound object. And then remember, if we want to convert to pounds, actually, let's not worry about converting to pounds in this case because it's going to cancel out. So initially, our momentum is 30 pounds. Usually, we want to plug in slugs, but pounds are okay in this case, multiplied by our 9 feet per second. And that's all the momentum we have. It's completely from our 30-pound suitcase. And then finally, what we have is, well, the 30 and 80-pound suitcase, the 30-pound suitcase and the 50-pound suitcase carrier combined together. Right now they're sitting together as one object, combined to be an 80-pound object, and we want to know how fast they are traveling, right? So we'll call it VA, the velocity we need to know for part A. Let's actually call that V2, because that's the velocity combined, and that's going to tell us about the speed of our object at time 2, which is what we need to find for our change in kinetic energy. So we know that these two must be equal from the conservation of momentum. So that means that this velocity of the suitcase, 30-pound suitcase, and baggage carrier combined immediately after the worker throws the 30-pound suitcase is going to be, let's see, we have 30 pounds divided by 80 pounds multiplied by the 9 feet per second. See, we hear our pounds cancel, so we don't have to worry about converting pounds to slugs at this point, and that's why I initially started and then I took it back because we needed to do it. And that means right after the 30-pound suitcase gets put on the baggage carrier, we have it moving at 3.375 feet per second. So that's going to be the speed of our combined 30-pound suitcase and suitcase carrier, 50-pound suitcase carrier, right after it is thrown. So if we take the difference in kinetic energies from this state right after the suitcase has been thrown onto the baggage carrier, and then right before that, so when only the suitcase itself is moving, we can get how much energy is lost. So in terms of variables, what is our total kinetic energy after the 30-pound suitcase has been put onto our object? We have 1/2 for our kinetic energy. It's 1/2 times the mass times the velocity squared. Well, the mass of this entire thing is 80 pounds because it's the 30 plus the 50, and then we need to divide this by our 32.174 pounds per slug to make sure that we convert correctly to mass to calculate our kinetic energy. Then we need to plug in our speed here. We just found that to be 3.375 feet per second squared. So this is T2, right? This is the total kinetic energy of our combined 30-pound suitcase and 50-pound baggage carrier moving at 3.375 feet per second squared. So we need to subtract from that the kinetic energy we had beforehand, which would have come from just our 30-pound suitcase traveling at the 9 feet per second squared. And then again, remember, we need to convert to slugs to get the right units of energy. Now, we solve all this out, plug it into our calculator, and you see that we get an energy loss of negative 23.6. And then what are our units here in this case is a foot times a pound, which makes sense because that's a unit of length times a unit of force, which is what we use for energy. So we lose, hence the negative symbol, 23.6 foot-pounds of energy when this 30-pound suitcase is thrown on the initially stationary 50-pound baggage carrier. Cool. Now, what's next? Well, we need to then consider what the energy loss is going to be of our entire system once we throw this 40-pound suitcase on. So let's make some room to look at that case, right? So it's the same setup. We need to find the change in kinetic energy, but the change in kinetic energy is going to be from two different states in this case, right? So it's not going to be state 2 versus state 1. Let's call them something different and new. Let's call them state 4 and state 3. So what does state 4 look like? What does the kinetic energy look like when all of these objects are together traveling at some final speed? Well, we know from the previous problem that no matter which suitcase we throw on first, the final speed of everything together, and so now we're going to go again and consider absolutely everything together now. So we're just in this system here. What is our total kinetic energy? Well, right after it's all done, when they're all together, we found out from a previous problem, I'll just write it down here, that the final velocity of everything, all of these together, ends up being 4.25 feet per second. So, from that, we can calculate the total kinetic energy of our system after both suitcases have been thrown on the suitcase carrier. It's going to be 1/2 times the weight of all these together. So we have 50 plus 30 plus 40. So we have 120 pounds. I believe that's correct. Yep, 120 pounds. Again, let's remember to convert this to slugs, 32.174 pounds per slug. And then we need to multiply that again by the speed at which this would be traveling. And from doing conservation of momentum in a previous problem, we figured that it was 4.25 feet per second. So that's the total kinetic energy of our system after all of the suitcases have been thrown onto the baggage carrier. Now, what is the kinetic energy of our system prior to that? Just prior to our 40-pound suitcase being thrown onto this carrier. Well, we know we still have the kinetic energy from our 30-pound suitcase and 50-pound suitcase, so 80 pounds of mass, well, 80 pounds of force. Divide that by 32 pounds per slug. That gets our mass. We have that much mass traveling. Well, what did we figure it out to be? Right? That was 3.375 feet per second squared, right? So when we throw the 40-pound suitcase on, we still have the 30 and 50-pound objects traveling at that 33.75 feet per second. That's still part of our kinetic energy there. So we also have that plus, right, we have our new instance of the 40-pound suitcase being thrown at 6 feet per second. Oops, let me write that better. 6 feet per second, all squared. Right. So after everything has been thrown on the baggage carrier, it's traveling at 4.25 feet per second, so it possesses this much kinetic energy. Prior to throwing prior to the 40-pound suitcase landing on our baggage carrier, we still have the 30-pound suitcase and 50-pound baggage carrier traveling at 3.375 feet per second, and then we're throwing that 40-pound suitcase onto it. So we have that kinetic energy from our 40-pound suitcase traveling at 6 feet per second. So we take the difference in those two things. That's going to give us how much energy we have lost in our system due to the change in kinetic energy, and we see that it ends up being here a negative 2.8. Negative 2.86 feet pounds. And then let me just real quick remember, I need to also convert this force of poundage here to a slug before the math will work out. But once we do that, we get our last answer here. So when we throw our second suitcase on, we end up losing 2.86 feet pounds. Oh, and that's should have changed this up here. Just to wrap this up, this should be AB. That's solving part B. So we solved part A previously, that we lose 23.6 feet pounds when throwing the 30-pound suitcase on the baggage carrier. Then if we immediately then throw the 40-pound suitcase on the baggage carrier, we end up losing an additional 2.86 feet pounds.